Hey everyone, and welcome. So if you're deep into a calculus course, you know that some concepts are just the absolute bedrock for everything that comes later. Today, we are diving right into one of those, 3D vector arithmetic. This is literally the language we use to describe our three-dimensional world, and getting a good handle on it is a major level up. So let's jump in.
So, to get us started, I've got a question for you. Think about your phone's GPS, right? Or the physics engine in the latest video game, or even an engineer figuring out the forces acting on a bridge. What is the invisible mathematical thread that ties all of those things together?
You guessed it, they are all powered by 3D vectors. And these aren't just some abstract numbers on a page. Nope, they are the fundamental tools we use to represent both direction and magnitude in the space all around us. So, understanding them isn't just about passing your next exam, it's about understanding how so much of our modern world actually works.
Okay, so what exactly is a 3D vector? Well, here's the good news. If you're already cool with 2D vectors, the ones on a simple XY plane, you're basically 90% of the way there. A 3D vector just adds one more piece to the puzzle, a z component. That's what gives us our sense of height or depth. Just think of it like an arrow floating in 3D space, and its coordinates tell you how far it goes along the x, y, and z axes.
All right, let's start building our toolkit. The best part about 3D vector math is how simple and elegant it is. Seriously, the operations you already know from 2D, well, they just get one extra step. There are no crazy new rules to memorize here. It's just a really natural extension of what you already know.
First up, vector addition. Let's say you want to add vector A to vector B. The rule is incredibly straightforward. You just work component by component. That's the mantra. You add the x's together, then you add the y's together, and finally you add the z's together. That's it. You get a new vector, and you're done.
Next in our toolkit is scalar multiplication. This is what we do when we want to make a vector longer or shorter, stretch it or shrink it without changing its direction. You just take a regular number, which we call a scalar, that's our c right here, and you multiply it into every single component of the vector. So that c gets distributed to the x, the y, and the z.
Okay, theory is great and all, but let's actually see how this toolkit works in the real world. We're going to combine both of those operations we just talked about into one problem, just to see how the rules stack up.
So here's our problem. We've got two vectors, A and B, and we need to figure out what 3 times vector A minus 2 times vector B is. Now, this might look a little messy at first, but all we have to do is follow the good old order of operations.
So, first things first, we got to handle those numbers sitting outside the vectors. We're going to deal with the scalar multiplication first. So, the game plan is calculate the new vector for 3a, and then calculate the new vector for negative 2b. And notice how I'm looping that negative sign in there with the 2? That's a really key detail that makes the next step way easier.
Let's start with 3 times vector a. We're just going to distribute that 3 into each part. So 3 times 3 gives us 9, 3 times negative 1 gets us negative 3, and 3 times 4 is 12. And just like that, there's our first result.
And now for the second part. We're calculating negative 2 times vector b. Now listen up, because this is a super common place to make a mistake. You have to make sure that negative sign gets distributed to times every single component. So, negative 2 times 1 is negative 2. Negative 2 times 2 is negative 4. And negative 2 times negative 5, that gives us a positive 10. And there's our second vector.
Okay, now that we've taken care of this scalar stuff, our problem looks a lot simpler, right? All we have left is a basic vector addition. We just need to add those 2 new vectors we just found, and we do it, you guessed it, component by component. And here it is, the final answer. For the x component, we take 9 plus negative 2, which gives us 7. For the y, it's negative 3 plus negative 4, which is negative 7. And for the z, 12 plus 10 gives us 22. See, breaking the problem down into smaller steps makes it totally manageable.
All right, let's shift gears to our next concept. We can actually use what we just learned about scalar multiplication to answer a really important geometric question. Are 2 vectors parallel? Which, just means, are they pointing in the exact same direction or the exact opposite direction?
Let's put it to the test with these 2 vectors here, a and b. Just by looking at the numbers, it's not super obvious if they line up, right? But luckily, we have a very simple algebraic test we can run to find out for sure.
Okay, so here's the secret. We just check the ratio of the components. For the x's, we take b's component and divide it by a's. So negative 6 divided by 2, that's negative 3. Now let's do the y's. 12 divided by negative 4, also negative 3. Okay, things are looking good. And for the z's, -3 divided by 1 is, you guessed it, -3. And because that ratio was the exact same constant number for every single component, in this case -3, we've just proven that these vectors are parallel. We can say for sure that vector b is just vector a stretched out by a factor of -3. And that negative sign, it just tells us that b is pointing in the complete opposite direction of a.
All right, for our final example, let's put all these skills together to solve a more practical, geometric-style problem. This is exactly the kind of thing you do in a physics or engineering class, where you know the direction you need to go and you know exactly how much force, or length, you need to apply. But first, we need one more quick definition: the unit vector. A unit vector is special. Its length, or magnitude, is exactly 1. Think of it like a pure direction pointer. It doesn't have any length of its own, it just says, go this way. We can make one from any vector, and it is the absolute key to solving our next problem.
Okay, here's our mission. We need to find a brand new vector that has a length of exactly 10, but points in the same direction as the vector v, which is 2, 2, 1. Here's our 3-step game plan. First, we'll find the current length of vector v. Second, we'll use that length to shrink v down into a unit vector. And third, we'll take that little unit vector and scale it up to the length we actually want, which is 10.
All right, let's do this. Step 1, find the magnitude of v. We use a 3D version of the Pythagorean theorem. So we square each component, add them up, and take the square root. That's the square root of 2 squared plus 2 squared plus 1 squared. So 4 plus 4 plus 1, that's 9. The square root of 9 is 3. So the current length of our vector is 3. Step 2, create the unit vector. We just divide each component of our original vector by that magnitude, 3. So we get 2/3, 2/3, 1/3. This new vector has a length of exactly 1. Perfect. Step 3, scale it up. We just multiply our new unit vector by 10, giving us our final answer, 20/3, 20/3, 10/3.
Whew, we have covered a lot of ground here, right? From basic addition all the way to scaling vectors to a specific size. So let's just take a breath, zoom out, and make sure we lock in the single most important idea from this whole explainer. Seriously, if you remember only one thing from today, make it this. For all these basic operations, adding, subtracting, scalar multiplication, the secret is to stop thinking about the vector as one big scary thing. Just focus on one component at a time. The x's only care about other x's, y's only care about y's, and z's only care about z's. It really is that simple.
So, you've now got a really solid foundation in the algebra of 3D vectors. But this leads to a pretty fascinating question, doesn't it? You know how to add them, you know how to scale them, but can you multiply two vectors together? And what would that even mean? Well, that's where really cool concepts like the dot product and the cross product come in, and they open up a whole new world of possibilities. Thanks for watching.